One thing we always do, we use internal timing buffers. Now, to do this, you have to use buffers. What this means is, internally in our own code, whenever I'm going to pass data from here to here, I don't just pass a variable. Instead, what I do is I load that data, kind of a name-value pair, into a buffer. I then pass the whole buffer over. The reason for this is, when I load it in or read it from a buffer, I can always remember to do scope checking, size checking, if I don't have buffer overflows. 2, in that buffer, I always put a timestamp. The part of the code that receives it looks at this timestamp. If it's too big, die. Why? Because if it's going slow, it means either the system's running really slow, and typically I'll put 10 milliseconds there and for our internal stuff, and internal operations like that are always microsecond level. So putting 10 milliseconds is a lot of time. But if somebody's coming at you with a debugger, it's going to be slower. If they put a breakpoint in there where you're passing data, this won't stop a good hacker, but it will slow him down a lot. Because he has to figure out how you're checking that timing and overcome it. So as I said, we timestamp everything. So what we do with so whenever we create a random value, a nonce, we actually put a timestamp on that. So if some encrypted data comes with a nonce, if the timestamp on that is too long, die. So we send an alarm and die. All of our buffers, any type of communication, whether it's internal in the code or through the network. If it's through the network, you have to put a longer timeout on it, of course.
How about the typical time to server?
So right, so if it's from client to server, then we have a longer timeout window. That's a window. And so basically, the client writes the timestamp, wraps the data in a buffer, encrypts that buffer, sends it to the server. The server receives it, checks the MAC, de-encrypts it, looks at the timestamp on the buffer. If it's too long, die. If the timestamp is okay, now you decrypt the buffer and parse the data from it. But it sounds like a lot of overhead, but it's actually, all of these are very fast operations. If your code is efficient, these don't add a lot of overhead, and they become huge barriers against the hacker. So, sorry, this text is very small, because I wanted to talk about, these are some of the methods we actually use in our own code. And I did do English and Korean for all of these. May be quite hard to read. I guess you're going to make these slides available to everybody, right? JP? Yeah.
If you allow.
Yeah, no problem.
Okay.
So I did this in both languages because some of the detail can be hard to catch. So part of what we do, so we have a protocol called attestation. So when our client connects to some site, that site sends us a kind of challenge. The first thing we do is we check with our main server and say, how about this challenge? Is it real? He comes back and says, yes, it's real, and here's the public key to talk to him. So now I get the public key, I can mix it with my own key and send the response back. Now, because I got that public key from someone else, and this server is the only one who has the secret key matching it, what I send in response, no man in the middle can possibly decrypt that. If I've done my job right in the protocol. So there's an implied registration between this site and the attestation server. So that has to be done well. But if that's done well, you can completely defeat a man in the middle, even to a new site. So I mentioned a scrambler. So our own system, we have all storage done in scrambled memory. So as soon as our app starts, we create a field of a few megabytes of memory, and we load that with random data. Just fast pseudo-random data. The quality of the randomness doesn't have to be high there. And then we create some unlinked pointers that point to random positions inside that data, so that as we bring in and get actual encryption, decryption keys, we store those in that scrambled memory field, so that any dump of that memory will be pretty much impossible to extract the keys from. We use a system we call TLE. So that's just a name I made up for total link encryption. Basically, whatever we send between the client and the server, we send using, so it's elliptic curve Diffie-Hellman ephemeral keys. So it's a Diffie-Hellman key system where I have a secret key and I know your public key, and I mix those together. I mix in some random value also, and now I send the data to you. You get it, you know your secret key and my public key, and know that random value also, and mix that in, and now you can decrypt it, and anybody in between cannot. So, as I mentioned, there's some random payload. Everything we send back and forth, some part of it is a random value, so that the thing we're encrypting is different every time. The secure wiping I mentioned, whenever we are finished using some value, we immediately securely wipe it. And we build all of our cryptography with constant time functions. This is becoming a big deal. Pretty much everybody in Korea uses RSA for the public key system. Yeah, what's called PKI, public key infrastructure. It's all based on RSA cryptography. It's all terrible against timing attacks. Yeah, come on, RSA is 25-year-old technology. It's just the algorithms for it were not designed to protect against timing attacks. So this will become a much bigger issue. So right now, the RSA key is 1K size, which is quite common still, are pretty easy to attack with side channel timing attacks. Especially because their random number generators are often not very good. Yeah, NSA hacked the NSA libraries to use bad random number generators. Within our system, any type of nonce, any type of the link, any type of challenge is always one use. So in our servers, we enforce that very strictly. That so we're an authentication protocol. So when the user asks to authenticate, he gets a link from the server. That link has timestamp, server ID, some random value. The server remembers that. So when the user comes back, he has to respond with that link. And if there's any variation there, or if it's a secondary use, if it's been used already, the server immediately drops the connection. So every type of use in our system, we very strictly enforce single use. So what that means is, on the server side, we have to maintain a list of everything and what status it's at. Okay, this one's issued, not yet used. Okay, this one has been used to log in, so no more use. But because by default, we put a 10-minute time limit on those, we keep this list, but then we just roll them off after 10 minutes. Because anything more than 10 minutes old is automatically rejected. So it doesn't eat up too much memory doing this. As I said, that's the here. Everything has, so if it's a login authentication or a payment authentication, they all work within that 10-minute window where the link is alive and active, and if it's not used, it just drops out of the system. It's impossible to use. So we do device binding also. The reason here is just, so as a user, you have an app. It's on your smartphone. Okay. So your super secret private key is stored in that phone. Yeah, it's encrypted. To decrypt it, you need a password. The password has some big, long function to make the key to decrypt it. But remember, we're on an Android phone. Somebody can get a keylogger. They can learn my password. So, if a bad guy can learn my password, and he can somehow get that file off of my phone, he puts it on another phone, it won't work in our architecture. That password, the way we mix the password to derive the real key to decrypt the data, is linked to some data which is internal to that device. So like a UUID or a SIM ID, so something like that. So that's, again, it's not a perfect barrier. If the bad guy knows if he knows, oh, they're mixing with UUID, and he can grab the UUID. If he can grab the file, he can probably get the UUID. So it's not perfect, but it's a lot better than anything else I've seen. So just little things like that cause, there's no performance overhead at all. It's trivial. We just actually add data like that, we HMAC it in with the derived key, and that operation is not expensive. One thing we do enforce is strong passwords. We don't allow the users to put in very short or very simple passwords. So, yeah, that's not so easy to enforce. The users find lots and lots of ways to make stupid passwords. I don't know, again, yeah, if any of you have looked at like the statistics on hacked password databases, I mean, I've got, I don't know, 10 million or so hacked passwords in my library. And so if I'm attacking a site or a user, yeah, first thing I do is go through all those passwords in my dictionary. And, at least 50% of the time I get it. It's actually shockingly easy. It's shockingly bad what bad passwords people use. Actually, way back in 1992, I built a crack library. And one of the things was I made a new kind of dictionary because a lot of Koreans thought they were very clever. They would, use the Hangul word typed into an English keyboard to make it looks like a gibberish password. Well, I made a whole library of those. It was really, I cracked, I think 85% of the professor's passwords at PlusTech doing that. So we put in a number of little things that to stop the decompiling and reverse engineering. So as I mentioned, we put the time trapping between threads. We encrypt all of the strings. So in our source code, we have strings. The strings and the variable name for those strings can tell the hacker something. Just by the string, you kind of know where you are in the code if you can find it. So what we do is before compiling, we take every string in there and we make an encryption key and we XOR the real string with the encryption key and store that. And every string we store is extended to maximum length. So we have a maximum length of 1K. So every string in our source code has a length of 1K. It's some random value. And to get the real string behind it, when the code's running, as it uses a string, it goes and gets the string value, XORs it with the key, gets the real string, and then applies it. Again, some overhead in the code, but the effect of this is when the bad guy looks at your binary, he sees a whole bunch of junk. It's really hard for him to figure out what's the key. No, he can do it. We're not, we're not being very clever with encryption here. We're just making it harder. A lot of these things, you cannot perfectly protect your code. It's going out there in some device. The bad guys can hack on it. But you make it harder and harder and harder for them. I mentioned buffer overflow, so we check all boundaries all the time, everywhere. One of the things we do in our app, any type of error in process flow and so on, the app generates an error and sends it to our server. So we can get some early warning if somebody's trying to hack on and play with our app. We can see exactly where in the code they're doing that. This is another thing we do. Every error code in our source is different. We never reuse a single error code. Right now in my code base, I have 7,000 error codes. Because I check every operation, and every time I make a new error code number. Now, again, I wrote some scripts to manage that automatically. I just write error XXX and put the description in the comment field. Then my script comes in, runs, puts a number on it, and takes the description and puts it in the proper header file. But the point is, when I get an error code, I know exactly where in the source code it happened. So for the app that's out there on users' phones, when there's an error, if it has network connectivity, it sends it to my server. I know, oh, somebody's attacking this app this way. So I can, I decide what to do then. That's a way to see it. Yeah, I won't talk about our locking. We have the ability to lock accounts pretty easily. key point in our architecture is that we don't keep secrets at the server. The biggest problems we've seen over and over again is some bad guy hacks into a server, gets the encrypted password database, but then can take it away and go work on it and learn all the passwords. Once he learns the passwords there, now I have a username password pair. Oh, I can go try that on a bunch of other sites because most users are stupid and reuse passwords. Right. It works shockingly well. Our architecture doesn't keep any user secret on the server. Our server keeps a user's public key. The user has his own secret key. So the user authenticates himself by cryptographically signing a challenge. So the server says, here's the challenge, which has the random number in it. The user uses his secret key to sign it. The server can now say, yes, you are absolutely that person because you signed this correctly. The server doesn't know the user's secret. All he knows is the public key. Stores that. This means that for a hacker, storing data in the server is a great target. You have to hack one machine and get millions of users. Right? And a couple of years ago, somebody hacked KT's website and got, 3 million user accounts. This happens over and over again. Right? Ashley Madison, lots of them. So what we wanted to do is say, okay, all the secrets are only in the user's device, under user's control. It means the hacker has to attack the users one at a time. His cost per user is much higher in that case.